5. Annoying. Yeah. The title, Indexing and Complex Queries. We just complete basic queries in module 4. So our next assignment, after you submit your homework assignment today or tomorrow, then this weekend, I will assign you homework assignment number 2. Number 2, mainly you'll practice basic SQL queries. We learned from module 4, okay, But after that, now we get to complex queries, okay, Much harder, but you need to work on basic queries first. After you have a lot of experience, then we move to complex queries, okay? But for the complex queries, I plan to split into 2 modules. So module 5, we will do 1/2 complex queries. Module 6, we do another 1/2, okay? Right. So in this way, we can stretch our practice time longer, covering 2 modules. And our final also, we will test on complex query questions. But don't worry, because usually when you work, you will experience that when you work on complex queries. Usually it takes a lot of time. You need to spend a lot of time, relatively hard. So for final, I plan to do this way. All right. We have 25 questions, right? 25 questions. In class, I just give you, in the final test classroom, we do in the classroom. In the classroom final test, I give you 20 questions. 20 questions. The remaining 5, that's the relatively hard, complex queries. I make it online. So you work at home, okay? In that way, you will have more time, less pressure, more time. In that way, I hope you can do better in those 5 hard, complex query questions. In class, I won't give you complex query question. I just give you basic query questions, okay? And, theory part, Theory part, here we start that part, indexing. So that's important, big part, All right, so let me start our first topic, indexing, introduction to indexing. 8.1, why using indexes? All right, so let me, Okay, all right. First, I like to talk about, think about when we use DBMS. When we use DBMS for large databases, okay, how large is it? So let's talk about, millions of records, that category, and the data size could be in gigabytes. That huge database. That's possible, right? In business, in real world business, that's possible, all right? Think about in that situation, when you need to search to find a record satisfying certain conditions, how fast, how much time do you need to find your answer? So searching operation, the performance of the search operation, extremely important. Yeah. So in this topic, we will learn the techniques, the basic techniques used to make the search operation very fast. Yeah. All right. So the name of the technique in indexing. All right. Using indexes. Yeah. What's that? We know the meaning of indexes in when we use arrays, right? When we use, many other things. But here in our DBMS context, its meaning is different. Yeah. So it has its own specific meaning. Yeah. If you look at from high level, there is some similarity. This indexing concept, our old indexing concept, there is some similarity. But in our DBMS context, we have a lot of specific details. Yeah. So we will put it in. Yeah. All right. Look at the reason we use this technique. Yeah. Speed up the retrieval of records in response to certain search conditions. Yeah. All right. But the question is how to do it. We know speed up, that's very important, right? Yeah. The response time, for a large database, extremely important. The question is, how do you speed up? Yeah. Try a little bit. Yeah. If you look at this question, do you have any idea how to make the search faster? Think about this general question. How to make search faster? Okay, think about that. Yeah. Here, you need to have a little bit algorithm background to answer this question. In algorithm, how do we make search faster? Yeah. Here, let me recall a little bit the algorithm background slightly. In algorithm, we learn search operations, right? Yeah. So here we have that situation. We need to apply that knowledge from algorithm here. Yeah. So let me review a little bit. In algorithm, search algorithm, all right? The first one, linear search. Second method, commonly used search algorithms. Second one, binary search. Third one, another very important search algorithm, hashing. Okay, yeah. I haven't covered in my algorithm class, but I will do it, yeah. Quickly, yeah. So, all right. In these three searching algorithms, linear search, very slow, all right? Yeah. We know its efficiency, big O of n. Binary search, very fast, its efficiency, big O of log n. All right. Hashing, extremely fast, big O of 1. Look at that, big O of 1, constant. That's the average case, not the worst case. Worst case, still slow, all right? Average case, so fast, all right? Okay, yeah. And here, in DBMS, the solution comes from these three algorithms. You can see these three, okay, yeah. Linear search, it is applied on unordered data. Yeah. It can be applied on unordered data. Okay. No limitation. Basically, you can apply on any data, right? Linear search. Okay. Yeah. Binary search must be on ordered data. Okay. Ordered data, binary search. All right. Yeah. In order to apply binary search, you need to make sure your data is ordered. Yeah. Hashing, no order requirement. No order requirement. What's that no order requirement? Even if your data does not have any order, the order of your data is not defined. In that case, we can still apply hashing. Yeah, I will go there. All right. Yeah, I will go there. Yeah. So that means, you know, it's a very general algorithm. Okay, very general algorithm. Yeah. All right. So that is the background. Yeah. In our indexing technique discussion, we need to use this background. So I review a little bit here. Yeah. All right. So let's start. Yeah. The idea. All right. Erase a little bit. All right. All right. Yeah. The structure of the data is important for the performance of data retrieval. What is the structure of the data? Yeah. The way you arrange your data. Okay. Yep. You have freedom. So here I mean the DBMS vendor. Yeah. You know, those companies, they make their products. So they have freedom to design these algorithms. Okay, yeah. So they can find efficient algorithms to arrange their data in a special way. Yeah. So we will see what kind of special way. Okay, all right. Yeah. But the original structure of data should not be changed. What's that? Original. What is the original structure of the data? That means, remember here, we are talking about a database. In our business, right? Yeah. In our business, okay, yeah. So we have a database in our business. Based on our business requirements, we need to store our data in some specific ways, right? That's based on the big business requirements. Okay, all right. That kind of structure for original data, we should not change. Yeah. So here, this item, the original structure of this should not be changed, because if someone changes that, it will impact your business. We don't like that happen. Okay? We do not want to make any negative impact on our business. Yeah. So here the situation, you can see, we want to speed up the search operation on our data in the database without changing the original structure. That's the requirement. If we change our structure, even if you can make the search faster, but you may put some negative impact on your business data. Yeah. Yeah. So that's not good. All right. All right. So here you see some limitation. Yeah. Limitation. Yeah. Original data you cannot change, but you have freedom to use auxiliary data. Not original data, supporting data. Extra auxiliary supporting data. How about that? Yeah. We keep the original data intact. All right. We do not touch that. All right. But can we create some extra auxiliary supporting data? Yeah, that's fine, right? Yeah, that part will help us improve the search operations. Yeah. That's the idea. All right. Yeah. All right. So may not, yeah. All right. So here, the meaning. Yeah. 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 Because here, the original structure may not be friendly for faster search. Why? Think about in your original data, the data may not be sorted, unordered. The data is unordered. That means if you apply search operation, you cannot apply binary search. You can only apply linear search. Then the performance is very slow, right? Yeah. So in order to apply binary search, you need to sort it. You need to sort your data, all right? But you don't want to touch your original table. Original table, because for some reason, they should stay in that way. Yeah. All right, yeah. So let's look at the solution. Create auxiliary access structure. We call that part indexes. Auxiliary access structure. The main purpose for the extra structure for accesses, for fast accesses. Okay, yeah, all right. All right. Based on indexing fields. What's that? What do you mean indexing fields? Right? Yeah. All right. Let me explain a little. Multiple indexes on different fields for the same file, same table. Now, let me use a diagram to explain the situation here. Suppose we have a table here. So this is our table. Okay. In this table, we have multiple fields, right? Field 1, 2, 3, and so on. All right. Yeah. All right. Yeah. Okay. Yeah. Yeah. So let me call field 1, F1, F2, F3, and so on. Okay. All right. Fn. All right. Yeah. All right. Here, indexing based on indexing field, multiple indexes. Yeah. All right. Because when we store the data in this table, then when you store the data based on which field you want to solve, yeah. Look at I post our case study example, university database. We have 5 tables, right? Yeah. I put a sorting button to ascending, descending button. When you click one, you sort it, but based on one particular field. Here we have same situation. When you talk about sorting, yeah, based on F2, F3, or F4. All right, yeah. Then the sorting result will be different. Based on field 2, you have one sorting result. Based on field 3, you have another sorting result, right? Different. You need to specify which field you want to sort your data against it, right? Yeah. So here it means if we want to sort our data based on field number 2, we can create an index 2, all right? Yeah. If we want to sort our data based on field number 3, we can create index number 3 and so on. In that way, we can have multiple indexes for one table. How about that? Okay, multiple indexes for one table. It depends on your need. if you need to do fast search operations for several fields, several table fields, then you may need several index files. All right, so that's the meaning here. Now, let me move to next. Now, index basics. Now, we want to understand the basic structure. How do we create indexes, index files? All right, why it can make the search very fast, and on large amount of data, the search is still very fast. Why we can do that? Yeah. Secondary access paths, not the primary, secondary, right? Yeah. Because we need to build it. Yeah. For the original database, it may not exist. Yeah. But indexes may not exist. You need to define, you need to tell DBMS to create those indexes, index files. Yeah. So the secondary access paths. Okay, not the primary. Yeah. All right. Additional files on disk. Additional. So here you can see the physical files, not the virtual files. You need to create derived data, yeah? Not original data, right? Yeah, derived. So based on the original database, derived data, yeah, and store new files on the disk. Each index, you need one file for it. Look at that. We know each table, you need one file, right? But here, each index, there is one physical file to store one index file. One index file in that way. So multiple indexes, you need to use multiple index file, physical files. All right, yeah. All right. Using extra storage space in exchange for better performance. You have to pay. Yeah, this extra space, that is the cost you need to pay. All right. Nothing is free, right? So here, you want to enjoy fast performance. But fast performance, this nice result, it's not free. You have to pay. So what is the pay? You need to use extra storage space. Okay, yeah. So that's the cost you need to pay. All right. Sorting can be used in those additional. Sorting can be, so here, yeah. Although sorting, that's the most frequent way we use to make our indexes. But you have the situation, you cannot apply sorting. You have some situation, you cannot apply sorting. So keep that in your mind. Yeah. The reason is that order property. Your data may not have the order property. Think about that. Yeah. So I will elaborate that order property later. Okay. So here you just need to know sometimes we cannot do sorting on our data. Okay. Yeah. Yeah. If we can, then we will be happy. Yeah. If we can do sorting, then that's nice thing we like to have. We can make our search faster, right? Yeah. But if we cannot do that, then hashing, we need to use hashing technique. Yeah. All right. does not affect the physical placement of records in the primary data file on disk. Yeah. So we keep that intact, all right? We do not touch that. Yeah. Our primary data, primary business data, all right? Yeah. We attach that. So each original table, we attach certain number of auxiliary index files, physical files. And if we want to make a fast search on our original table, we can work on our index files to get a fast search result. That's the basic idea. How to make that happen? Yeah, then we need to spend a lot of time to learn the algorithm details to make that happen. All right. Indexing fields. All right. Basically, any field of the file can be used to create an index. Yeah. Basic, any field. Okay. Yeah. All right. Yeah. If you like, yeah, any field you can use to create an index. Yeah. But the way to create could be different. Yeah. Sometimes you use sorting, sometimes you use hashing. Okay. Yeah. If you cannot use sorting, you can use hashing, right? So here, yeah, we just put these two ways to create indexes, sorting or hashing. All right, yeah. Sorting is the primary way, the dominant way, okay? Yeah, most of the time we use the sorting to create indexes. But hashing, the minor way, yeah, yeah. The percentage, the chance very small. Okay, yeah. All right. Non-necessary, those fields with total ordering. Yeah. So here, there is a concept called total ordering concept. Yeah. What is total ordering concept? Yeah. From the name, you can see its meaning in a straightforward way. Yeah. Total ordering. So here, let us talk about field. A field of data, okay? Because when we talk about ordering, usually we talk about a particular field, okay? Yeah. Birthday, age, right? You know, social security number, one particular field. Yeah. All right. Then we have this concept, total ordering concept. So what's that? Any two data items in that field, we can compare to find the order using less than, equal, greater than relationship. Okay, yeah, we can find this kind of relationship. Okay, between any two data item in the field. That's total ordering, all right? Yeah, total ordering, no restriction. Yeah, you randomly select any two data items in that field. You can always find this kind of relation. Either the first one less than the second one, or they are equal, or the first one greater than the second one. All right. If you have that property, that means this field has the total ordering property. Okay? Yeah. And you may not always have total ordering for your data fields. Sometimes you may not have that. Okay, yeah. There is another possibility, that's the partial ordering. Related to total ordering, there is a partial ordering. So what's that? Still, let us select two data items in one particular field. Okay. Sometimes we can do comparison, sometimes we cannot. Okay. Sometimes we can do comparison. Sometimes if you do compare, you can not get less than, equal, greater than any one of them. You won't get any one of the three possible relationships. You cannot. Okay. Sometimes, yeah, partial ordering. Okay, partial ordering. Yeah. But in the real world, at this point, you may not be able to understand how can you get anything like partial ordering in the real world. You cannot do comparison. Here, let me show you that possibility. Yeah. It may not be very common, but it exists. Okay, all right. So here, let me draw a diagram. Small diagram. A point, B point, all right. Here, let us define if we have an arrow from B to A, we define B greater than A. Okay, so we define our relationship in this way. We define a relationship between A and B if there is a arrow, a pointer, start from B and end at A, we mean A greater than B. All right, yeah, here, look at that. Okay, here, C here, okay, C greater than B, so there is an arrow. All right, D here, all right, yeah, D greater than A, there is an arrow. All right, arrow, all right, C greater than D, there is an arrow, like that. All right, so I draw this diagram. All right, and I define order. Yeah, that arrow, I use that arrow relationship to define the order. Okay, it's legal. Yeah, by the order definition, this special definition is legal. Okay, all right. Now the question, look at the relationship between B and D. Can you tell me which one is greater, which one is smaller? B and D. No arrow, right? No arrow from B to D and no arrow from D to B. That means for this diagram, it does not have the total ordering, all right? But it has the partial ordering. It has the partial ordering. Okay, yeah. For some of the elements, you can do comparison, but for some of the elements, you cannot do comparison. Okay, that's the meaning of partial ordering. Yeah. All right, so here for indices, yeah, even if some of your fields do not have the total ordering, you can still create auxiliary index files for those fields. Why and how? Remember hashing. Hashing technique does not rely on ordering. Hashing technique, you will see, later you will see, it does not rely on ordering, any ordering. Okay, we don't need that. Hashing, it relies on mapping. Okay, mapping, some special mapping. Okay, the mapping, we do not need to compare which value is larger, which value is smaller. That kind of comparison is not needed when we create hashing data structure. Okay, all right, so we will do more discussion on that. Okay, hashing. All right. Some indices do not use sorting. Yeah, hashing, right? Yeah. All right, so that's the 8.1. 8.2, data structures for indexing. Yeah. Here we will learn more and more details. First, we start with relatively simple structures. Yeah. Ordered files. Let's look at how to define indexes on ordered files. Here we can do sorting. Yeah. So we have some easy way to define indexes. Yeah. All right. Require total ordering. Yes, this one, ordered file. Yeah. Because, you know, we need to apply sorting. Yeah. The ordering property, total ordering property must be there before we can apply sorting on it. Okay. Use the binary search. After we sort the data, the next thing is binary search. See? Binary search is so simple, right? Yeah. Everyone is familiar with binary search. So powerful in the real world application. So powerful. The reason for large database, the search operation is still so fast, binary search plays extremely important role there. Okay, yeah. Okay. Most prevalent types of indexes. Yeah, so this kind of, you know, total ordering, binary search based indexes, that's the most prevalent type. Okay, yeah, yeah, 90-something%, let's say in this way. Okay, yeah. So this simple way, it covers 90-something% of the usages. All right, yeah. The remaining, yeah, we have to use hashing. Remaining, no total ordering. We have to use hashing technique. Yeah, only, you know, very small portion. Okay, yeah. All right. Tree data structures. Yeah. The binary, even we use binary search, then sometimes we need to arrange our data in tree data structure. Why? Because tree data structure, yeah. So here, there is a, you know, so here, line data structure. Yeah. Line data structure is different from tree data structure. Okay. Your data is arranged in one line. It's sorted, right? One line. Okay. Yeah. So line data structure. Array, right? Yeah, one line, yeah. Data structure. Okay. But the line data structure, it has some obvious drawback. Yeah. That is, when your data size is huge, your line could be very long. Okay, very long. All right. Even you apply binary search, you need to do, you know, comparison many times. Right? Think about that. Okay. Yeah. All right. In that way, if you, yeah, because the line, this structure, it's a single levels. It has only one level, okay? Single level. All right. This tree structure, you have many levels, right? Top, down, you know, from root to leaf, the bottom, so many levels. So this is a multi-level. Multi-level structure. Okay, yeah. For the multi-level structure, you can handle large data size because you organize your data in many different levels. Okay, each level, you only need to do one comparison. You can go to next level. Okay, In each level, you do not need to do many comparisons. You only do one comparison. Then you go to next level. Another comparison, you go to next level, and so on. Okay? Yeah. So the number of levels you have, that the number of comparisons you need. Yeah. Even if you have large amount of data, still you can control to make the number of comparison relatively small. That's the essence of this multi-level structure. Okay? Later we will learn this multi-level data search. Data search. We will do computation. Okay? We will, do calculation given the data. Yeah. So we have many questions. We need to do calculation. Okay? How many comparisons we need to do in order to find certain data item? Okay. All right. Multi-level indices. Yeah. All right. Dynamic structure. Yes, another property. Dynamic structure. So what's that dynamic structure? All right. Your data. We know our data keeps changing, right? Data coming in. You keep adding new data items, but sometimes you delete data, right? Yeah. Some data you modify it, then later you delete some of the data. Come and go, your data. Keep changing, come and go. That's dynamic. Okay? Yeah. So here, in order to handle dynamic data efficiently, you need to make your index structure friendly for dynamic data. Friendly. Yeah. So what do you mean friendly here? Friendly basically means when you do any change in your index file, the changing cost is relatively low. That means friendly. You do not need to do too much work. Right? Yeah. If you do too much work, the cost is so high, that means not friendly, right? Yeah, the cost is too high, too slow. Cost high means the response time also very slow. All right. Yeah, that's not friendly. Yeah. You want to make the modification of your index structure extremely fast. Yeah, just as a few local change, yeah, not changing everywhere, many different places, just small area of the data, make some change. Yeah. All right. Hashing. Yeah. Fast, but no order information. Fast. Yeah. As I mentioned, hashing actually is much faster than binary search. The binary search, big O of log n, right? Yeah, log base 2, big O of log n. And the hashing, big O of 1. Okay, so much faster than binary search. Right? Yeah. Then binary search. All right. Yeah. So then, but the second half, but no order information. Yeah. It is fast, but it has drawback. The drawback, it does not support any order of the data. Okay. Yeah. That means, although you can find data fast, but if you need to do some operations based on order, then it won't be good because there is no order information there. Okay? In your hashing data structure, the order information is not maintained. Okay? If you want to apply ascending order, No, it's not good. All right. It's not good. All right. Yeah. All right. Yeah. That's the reason why the binary search based indexes is the most prevalent, right? Yeah. Its search speed is slower than hashing. Searching speed of binary search is slower than hashing, but it is still more prevalent, right? More prevalent. Yeah. So people like to use binary search based indexes much more than hashing because the binary search still maintains that order information. Order information, we know it's important. We don't want to lose order information, all right? Yeah. Binary search rely on order information and it maintains order information, okay? So we won't lose order information if our indexes are based on binary search. Yeah, so that's the good property. Yeah. All right. How indexing works. So let me give you some simple description. To find a record in the table, what is the fastest way to find the record in the table? Here, I want to disable my remote control. No. Yeah, here, let me actually, this description that reflects the essence of this indexing technology. Why we can make indexing technology so fast. Yeah. This slide explains the basic idea. Okay. A search condition based on a field. Yeah. Yeah, because when people make the search, all right, yeah, you need to specify, based on which field, all right? Especially ordering, right? When you want to describe ascending these, do you need to specify the field? Yes, you have to specify the field. Then you can do ascending, descending order, right? Yeah, here. Yeah. Assume that an index is created on the field. Yeah. So then we can apply binary search, right? Yeah. So, all right. The index is searched. So look at that. So our goal, we want to find a record. So this is our goal on the original table, okay? Original table. But if you apply search directly on original table, it could be slow. If the table is large, it could be slow, right? Yeah. You have a huge, big table, right? Yeah, could be slow, all right? So here, we want to do some extremely fast search, all right? Because we assume index is created, all right? For that table, one particular field, we already have a index created. That index, we can assume we sort the data based on that field, so we can apply binary search there. All right, yeah. So now, when a user asks for a search, we do not search the original table directly. We search our index with the given key in the field. Yep, we have the key, all right? Given key, we can apply binary search on the index file to find the location of that key in the index file. Yeah, we have a location in the index file, not the original file, in the index file, that location. Okay, yeah. After that, the search result of the index, yeah, the search result tells you the location of, yeah, here, let me give you, search result tells us what? Gives us a pointer to the disk block that contains the original requested record. Okay, yeah. Original requested record in the original table, yeah, it has a location on the disk block. Okay, that information can be accessed from a pointer in the, this pointer is in the text file, index file. Index file, all right? So index file, the structure is key pointer, all right? Key pointer, the structure, okay? But key given, right? Yeah, search key. Key given. With the search key, we apply binary search, we can find this entry, right? Yeah, this entry. Entry in the index file, in the index file. All right. Then, with this entry, we can retrieve the pointer, right? Yeah, there is a pointer, okay? This pointer points the location, this block location of the original requested record. Look at that. Okay, so pointer, yeah, tell us where to find the requested record. We just jump there, retrieve that disk block, load into memory. That's how we find the record. Okay, that's how we find a record. All right, yeah. So this is the first round explanation, not enough. No, no. Do not worry if you do not have very good understanding on this part, because later we will use many diagrams to understand these procedures. Yeah, all the details. Yeah, we use diagram to understand. Okay, yeah. This is the first view of this technique. Okay, all right. Yeah. Let me see how much time I have. Oh, 10 minutes I have. Yeah. All right, 10 minutes. So let me just go to 8.3 primary index. Yeah. Let me just go one slide of primary index. Yeah. Because this type of index, simple and very important, and it is used most frequently. Yeah. Most popular, prevalent. All right. Yeah. So we learn this first. Yeah. Okay. Simple. Yeah. But very useful. All right. Yeah. All right. Structure of the primary index. Primary. Yeah. Here. Yeah. We know. The meaning. Yeah. Most commonly used index type. Yeah. Primary. All right. That kind of meaning. Yeah. It may not relate to our primary key directly. Yeah, it's primary key. We have a concept, primary key. Yeah, related. Yeah, but a lot of difference between these two concepts. Yeah. All right, and order the file whose records are of fixed length with two fields. Here we are talking about the index entry structure. Each entry, a key and a pointer. Okay. Yeah. Here we have described an entry of an index file. Okay. All right. Yeah. Entry. Right. The structure, one key, okay, search key. Now, you need to have a search key. Otherwise, how can you do the search, right? So that key, you need it. All right. Then that key connects to a pointer. Pointer from previous slide, it points to the location, right? Yeah. The location of the requested record. That pointer, all right? Yeah. Okay. But that is the fixed length, okay? Fixed length. Why fixed length? All right. Think about fixed length. So each entry has the fixed length. Then you can manage your entries easily, right? You can make good prediction, right? Yeah, because you can jump, you can do calculation. For example, I want to go to entry number 10,225, right? I have that entry number. I want to jump there. With fixed length, you can jump to that location quickly. Think about with variable size, how can you jump? You cannot jump, right? You cannot predict. Yeah. The size varies. Sometimes longer, sometimes shorter. How to make good prediction. Yeah. So this fixed length also nice property for fast search. Okay, yeah. All right. Primary key of the primary index. Yeah. The primary index has a primary key, all right? Yeah. But this primary key here, the confusing part, because in our table, we have primary key concept, right? Here, in our primary index, we have another primary key concept. Yeah. Do not get confused. They are different. All right? The meaning of, so here, because the context is different. When we use the table context, when we talk about primary key inside one concrete table, we know its meaning, right? But here we talk about primary key inside primary index. Its meaning is different. Yeah, do not get confused. The why is different. Yeah, so we try to understand that part. Yeah. Why primary key here different from primary key there? All right, yeah. All right, so what is the primary key? The first field is of the same data type as the ordering key field of the data file. All right, yeah. Yeah, same data type as the ordering key field of data. Yeah. All right. No. All right. Actually, the meaning is straightforward. The meaning is straightforward. Yeah. Here, although I can draw the diagram to explain that. Yeah. All right. Yeah. We have only 6 minutes left. Yeah. We only have 6 minutes left. Let me leave this explanation next time. How about that? Yeah, right? Yeah. So, all right. So we are here. Yeah. So we do explanation here next time. Okay. Although the concept is not hard to understand, but just confusing, right? The primary key, first field, ordering key, you know, data file, that kind of thing. We just want to, you know, make very clear, you know, so what's the meaning? All right, you know, no confusion. Yeah, so, all right, yeah, so I like to draw a simple diagram to explain what's the first field, what's the, you know, ordering field, primary index. All right, yeah. All right, yeah, let me stop right here. Yeah. And next thing, you try to complete the homework assignment number 1. Okay, yeah. With that 1 day grace period. All right, yeah. Okay, try your best. Yeah. All right. So let's stop right here. I have a few more slides, so I will complete it next time. Yeah.